Hello everyone, today we will talk about the logic gates and its functionality. So what is logic gates? So logic gates will give you output based on some inputs. It turns on when a certain condition is true and off when the condition is false. Whenever we are saying true or on, it means digital 1. And whenever we are saying false or off, it means digitally 0. These are the types of logic gates, and in the next slide we will show you a video about the basic of the logic gates.
Logic gates. Logic gates are the building blocks of digital technology. There are many types of logic gates, which all work in different ways. This is a NOT gate. The output is always exactly the opposite to the input. This one is an AND gate. It needs both inputs on to work. This is an OR gate. It has two inputs. And either input, or both, need to be on to give a positive output. This is an XOR gate. Either input, but not both, needs to be on to get a positive output. Crikey!
Okay, so this is the symbol of a NOT gate. So it has only one input and one output. Sometimes we call it a inverter, you see, and we express it like a bar. So if the input is a, the output is a bar. It's always an invert, and this is the truth table. So next one is the AND gate. So this is the truth table of a AND gate, and this is the symbol. So it has two inputs and one output, and we write it like this: a dot b, but we pronounced it as a and b. And the next one is OR gate. This is the truth table of a OR gate, you can see, and for this case we write it like this: a plus b, but we pronounced it as a or b. And you can represent that these two circuit with these two gates. So this is the AND gate configuration of a circuit, and this is the OR gate configuration. And NAND is just a inverted AND gate. That means what are the NAND output is totally opposite of a AND output. You can see this is a AND output, and if you have a NAND gate, that will become 1 if the both input is 1 or both input is true, then output will be 0. And if the one input is 1, then also output is 1, that means true. So it's a totally opposite of a AND gate, and we write it like this. So a and b bar, like this, a and b bar, and this is the symbol. So you can see this is an AND gate, then we put an inverter over here, that's that NOT gate, and it became a NAND gate. That's why we have a circle at the output of a AND gate in a NAND gate symbol. Similarly like AND gate, NOR is a opposite of OR gate, and this is the output of a NOR logic gate, and you can see the symbol like this, a plus b bar, and this is the circuit representation. So XOR is little bit different than OR. It's not a totally OR, but you can see either of the input is on but not both, then the output is true. You can say it like in another way. If odd number of input is true, then output is true. And we write it like this. So A, then a circle sign plus B. So and this is the symbol of a XOR gate. And then is XNOR. So XNOR is just opposite of XOR. So you can see in XOR circuit we have output over here 1 and 1, but for XNOR is 0 for these two cases and 1 for these two cases. In another way you can say if the input odd number of input is if true, then the output goes true for XNOR cases. And these are the circuit representation of each gates. So with a true transistor you can make each of the logic gate. And here are all the gates. So these are the expression, these are the symbols, and these are the truth tables. And another interesting thing is with the NOR gate, only using a NOR gate you can create any of the gates. Like this one, in the first case, with the single NOR gate we create a inverter, which is NOT gate. And with a 3 NOR gate with a different circuit configuration, we create a AND gate. And here we create a OR gate. Similarly, like NOR gate, we can also produce some other gates which only using some NAND gates like this. And for these, actually NOR gate and NAND gate are called as universal gates. And these are the circuit, or these are the ICs of some gates. In the first case, this is 7408 is a AND gate IC. This is OR gate. This one is NOT gate. This one is NAND gate. This one is NOR gate. And this is XOR gate. And if you see the IC pin out diagram, you can see for the NAND gate, these two are input and this is output. Similarly, this is input, this is output. So in each IC, actually we have 4 NAND gates, and this 7 number pin is ground, so you should connect it to the ground, and this is the power pin of the IC, which is called as VCC. And for these cases, these are all similar. You can see 2 inputs, 1 output. Here is a little bit different. 2 and 3 is input, this is output. And for only the NOT gate, as it has only 1 input and 1 output, so in each IC we have 6 inverter or 6 NOT gate, and the power pin and the ground pin are same. So what we learn, logical function can be expressed in several ways. One is in truth table mode, logical expression, graphical form, and one of the example is the majority function. So let's see this one. So this is actually the 3 input majority functions truth table, and this part is the graphical representation, and this is the logical expression. If you see from here, you can also draw a circuit. So first of all, we have A and B. Actually, if you don't see any dot, that represent actually as a AND format. So A and B. So in the first, this is a AND gate, right? So we are getting input from here and here. So that means this is A this is B, and the output of this gate will be A, B. Similarly, like this, we are having B, C over here, and for this case we are having A and C over here, and we can see that there is plus sign. That means it's a OR combination. So we have to put these three output in a OR configuration. That's why we are taking a 3 input OR gate, and this is the actually output function. So here we are getting AB plus BC plus AC. So like this you have to from a logical expression you can derive a graphical representation. And these are some law. You'll get more info or more details about this law in our theory classes. So that's all from this part.